All right, last time, what were we talking about?
Isothermal processes and delta U.
Yep, so we're gonna rehash that really quick. What's meant by the term isothermal again? Yeah. Isothermal process, constant temperature. What's delta T equal to?
0.
Yep. Because there's no change. And I said from statistical mechanics, where that's where you look at kind of a combination of thermodynamics and quantum chemistry. Things are quantized, and you assume things are made of little particles. What you can find for a monoatomic ideal gas is the internal energy of that system is equal to 3/2 N RT. And we looked at delta U. Delta U is what minus what? Yeah, U final minus U initial. And what we could do is we could plug in what we would calculate for stat mech. Where really we're, in this case, we're only changing the temperature, we're not changing the number of moles. We would get that expression. How could we simplify this? Yeah. Okay, if we have an isothermal system, what was delta T equal to again? 0. Yep. So therefore, what is delta U equal for an ideal monoatomic gas? Yep. So sometimes it's very beneficial to utilize that assumption. You can say monoatomic ideal gas, bam, isothermal things are 0. There are some situations where you can't do that. Could you give me an example of a system that could still be an ideal gas, or you could assume ideal behavior, but it is not monoatomic? So what up on that periodic table would this not work for? Yeah, oxygen, O2, right? Wouldn't work. Give me something else. Hydrogen, yep, wouldn't work. What would work? Yeah, helium. Helium's a great one. It's tiny. What were you saying, Lily?
Noble gases?
Yeah, any of the noble gases. The lower ones get kind of weird, and depending on what pressures you're talking about, but yeah, in this class we can see. What is it? Xenon? Does anybody know what that name means? So all of them have on at the end of them except helium. On, if you translate it, means 1. So there's one that's called the hidden one. Xenon is the weird one. That's why I like it. I also think its name sounds like a demon. All right, so let's look at some situations where we can utilize this to our benefit to solve for something that we're interested in. So, question, what is the heat exchange? For a monoatomic, ideal gas, if a change occurs under isothermal conditions. What equations do we know that utilize heat exchange? We got a couple of them. Let's fall back to the most basic one we know. Which one incorporates Q?
U equals Q plus W.
Yeah. Delta U is equal to Q plus W. Okay. We have isothermal conditions. What happens in this case? What's delta U equal to?
Zero.
Yeah. Ideal monoatomic. So delta U is equal to 0. That means Q plus W is equal to 0. If we wanted to solve for Q, what's Q equal to then? Yep. Making it easy to find other things. Okay? Everyone sees somewhat of the utility of this. Okay. We needed to get to this point so I could prove to you something that we've just taken for granted so far. What type of function is Q? Yeah, you're right, Tessa, it's a path function. I told you it's a path function. Did we ever actually prove it was a path function? In order to do that, we needed heat capacities, and we needed to understand that isothermal processes and delta U. If we look at a monoatomic ideal gas, what is their